All right. Looks like we are ready to start. Good afternoon, everyone. So the AIA New York Building Science Committee is very excited to have you attend the first summer event for the year. Today's webinar is called Beyond Efficiency: Ecosystemic Approaches to Buildings and Public Health, which will be presented by researchers at the Yale Center for Ecosystems and Architecture. A bit about YLC. YLC is a collaborative center that includes the Yale Schools of Architecture, Art, Environment, Medicine, Nursing, Public Health, and Engineering and Applied Sciences. From the microscopic to the telescopic, their methods aim to bolster biodiversity and resiliency through clean life, supporting energy, sustainable water capture, and renewable material production. Directed by Anna Dyson, ELC unites researchers and practitioners across multiple fields, synthesizing innovations in science, art, the humanities towards ecosystems that prioritize the requirements of living organisms and ecologies. Their mission is to transform the DNA of the built environment, which is currently the sector responsible for the largest real-time climate change impacts and the consumption and production of toxic, non-renewable resources. So today we are joined by the founder and director of YLC, Anna Dyson. We're also joined by postdoctoral researcher Mandy Pretorius and architect researcher Christina Chardullo. Please note that we'll have a Q&A session in the last 10 minutes of the presentation, but please feel free to drop in your questions beforehand using the Q&A tab at the bottom of the screen. Please also note, please also note that the link for CS credit will be put in the chat towards the end of the presentation. With that, I would like to hand it over to Anna. Yep.
And thanks so much, Krishnav, and thank you very much for your invitation to present to AIA. It's an honor, and we always love to connect with our fellow professional architects because the center really is an outgrowth and kind of a version 2.0 of CASE, the Center for Architecture, Science, and Ecology, which we co-founded with our partners at SOM. And the real mandate of that center was to accelerate the deployment of and adoption of widespread adoption of disruptive technologies or technologies that could really be game-changing from the lab to the to practice. And I think our center now is continuing that mandate, but maybe the sort of 2.0 part of it is that we're working more and more with living systems, hence the term ecosystemic. Next, Christina, thanks. Yeah, so do you want to weigh in on this, Christina? Yeah.
Sure. Yeah, we will see these learning objectives when you registered, but we're discovering the role of living and non-living building systems in public health outcomes, identifying how building systems can quantitatively and qualitatively shape ambient resources, analyze multifunctional performance trade-offs, and evaluate social and environmental factors. And today we're going to be looking at 3 different system areas in energy, air, and water. And Anna, if you want to.
Yeah, sure. This is a great diagram that Christina put together. That it just shows the interrelationships between the way that we parallel track. As I said, the projects would be building projects. So if anybody has building projects that really could have the ambition to have a kind of next gen system with frameworks, and the frameworks are then research related to research areas of inquiry. So all of our systems are looking at the nexus between energy, water, material life cycle, air quality, et cetera. But we tend to sort of really drill down on each of these areas in specific ways, which we'll show in a minute. Next. So this is an image actually, and I think it's actually of an older system that we've fully sort of demonstrated, and we actually deployed this system and have licensed this system. A subsidiary of our AEC partners is deploying this now, but it's showing an image, and if you could imagine conceptually what would happen if we could shade with transparency. I mean, lots of different systems try to do that. So they redirect, they disassociate the solar heat gain coefficient from visible transmission by basically allowing diffuse beam to flood through across a building envelope and allowing and capturing, let's say, that energy or redirecting it, the direct beam. But this is basically what this first system that we're going to show you is doing, is that with glass and with less than 1% the semiconductor of regular solar facade systems is doing a lot of different things. Next. That's a system that we'll show you, but just a few words about our center is we are really intersecting on, as we said, all of these different fields. But one of the things that we try to do also is create new types of frameworks for learning. So one of our frameworks is called SEVA, Socio-Ecological Visual Analytics, and we have Beam Lab, Built Environment Ecosystems Measurements Labs, and you're looking at an image of a group that's getting together in Beam Lab, and you can see the physical model in the foreground, but then you can also see a fully immersive environment that's actually enveloping, wrapping the whole room. And so we're very, very keen with all of our both architectural and scientific and engineering partners on developing these new ways to look at the environment and new ways to zoom in and out of scales, inhabit other terrains, and really understand the ecologies within which we're working. So immersion is a huge tool that we do. This is the first Beam Lab that we built. We have another Beam Lab in Shop Architects, our partners at Shop, that we built there, that has been really, really effective in communication and development and also client interface. We recently demonstrated the first pass of our Drought Resilience Observatory in Saudi Arabia in another Beam Lab, and we will be demonstrating the Beam Lab concept also at COP30 in Brazil this November. So we do a lot of sort of international events where we're having a lot of people come around the table to look at the interface between ecosystems and built environment. Next. Another thing that we do a lot of are demonstration sites with small structures. So this is a structure that we were collaborating with Oak Ridge National Labs, Shop Architects and Branch Technologies on a very large scale 3D print from agricultural bio-waste. In this case, it's bamboo, and we have other systems with coconut and soy and mycelia. So this was for a biomaterials pavilion. And so we're looking at that relationship between computational and material systems. And we have a lot of demonstration sites where we like to have the public come and touch and feel new types of structures. And this, at the time, this is already more than 10 years ago, but it was the largest 3D print in the world at that time, certainly largest out of bio. It's currently at our partners in University of Nairobi, and so we're testing sort of the weathering and the durability of these sort of materials that could potentially replace completely concrete and steel. Next. This is a snapshot of our first large laboratory and new lab. You can see a lot of different prototypes around the room. We invite you all to join us at the launch of our next space in New Haven, which is we're going to be holding a symposium on the 8th, 9th, and 10th of October, and we will definitely let the AIA know about that. But we'd love to have you join us. And as you can see, we will be demonstrating a lot of different things. Here you can see the icy solar facade, which I'm going to be presenting in a second, and in the window in the background, that's the solar facade system. And in the foreground, you can see another system that Christina is going to be presenting, which is a bioremediation system using plants. Next. I guess it goes without saying that like all of you are professional architects and engineers and building professionals, and you know that it takes a really, really extensive number of people to come together. I would say the only difference in what we do is that we have PhD and postdoc programs where we're involving a lot of biologists, chemists, so that biochemistry and sort of the biochemistry of the built environment is fundamental to everything we do at multiple scales. And so there's a lot of other living system scientists that we're including in addition to the usual consultants that you would all have in a conventional architectural environment. Next. Shout out to our sponsors. We are funded often by the federal government and also by international sponsors such as the UN and the UNCCD. The Climate Change and Desertification Program is a huge sponsor of us currently, but we have historically been sponsored by many AEC partners, material producers such as Saint-Gobain is a huge sponsor right now too, who is going to be sponsoring our pavilion in Belém, and others over the years. Next. AIA was there, as you noticed. AIA has sponsored us for many projects, and we're hugely grateful. So thank you for that. I think, Christina, we can just go forward into the first system. Yeah, I think just because we're going to run out of time. So just really quickly, because maybe a lot of people have seen this system. This is we've been working on this area of inquiry. So we have areas, as we said, and this is the first instantiation of this area of inquiry that we've been at for over 25, actually over 30 years now, which is how do you really basically create modules and systems for the building environment, for the building envelope that would turn the building envelope essentially into a transfer function. So if you go to the next slide, you can see this is where we're testing basically a very large curtain wall unit. This is at the Center for Excellence in Environmental and Energy Systems. What we're basically trying to test is how much can we interface with all the energy coming through to deliver for systems on the interior. So that means that a building envelope doesn't just need to generate, let's say, power. It doesn't need to necessarily just transform the thermal environment. We are also looking at literally concentrating heat coming through so that we can take it off as high quality heat so that it can drive systems, it can do everything. So we're changing the quality of energy. Obviously, light, cool, diffuse daylight would be one of the most important things for health and well-being and what you would want to do with that energy. And of course, so a system like this is doing all of these things. It's a combined heat and power at over 70% efficiency. Christina gave the title of this talk as Beyond Efficiency. So we don't want to just beam count the photons and electrons around the room. We want to say, are we giving beautiful daylight? How much daylight? Are we taking the heat off and being able to redirect it or store it for really usable purposes? Not just hot water, maybe that would be the lowest hanging fruit, but potentially drive cooling with a higher temperature heat. So this is a sort of, very, very ecosystemic system, even if it looks very mechanical. Here, this is looking at a video inside our ecological living module. So next. We can probably go quickly through these next ones. I'm going to skip through this. This is just to say that we are looking at the ecosystem at all the scales, all the way down to nano. So these are systems that are literally nanotechnology. They're optical, it's semiconductor, it's all of these things coming together. Here's that's another view of another version of this system in New Lab. That was actually the window that you were just looking at. And this is a diagram. We love to call this the ketchup and mustard diagram, which is a shorthand. But what it does show you is we need to be treating light and heat very differently, and we need to be parallel tracking, like the taking energy off of the facade in forms that are not necessarily coming in the way that we want to and the way that we want it in the form. So there has to be this kind of redirection through the entire building, and that's where we're kind of being counting the photons and electrons around the building so that we can literally get to net zero just with the incoming solar energy. As you all know, conventional systems are probably 14% efficient at best if they're being well maintained with a conventional solar panel, but it's really only doing that. So you can imagine it's wasting all of the rest of the heat. Sorry, all of the energy is lingering around the building as waste heat if you're in a conventional sort of hot, humid climate like we are in New York City. So you might actually have a net negative with a lot of solar panels, depending on the way that they're installed. They might be heating up your building when you're trying to actually take electricity off or other things. So this is really giving you the principle of all the systems that you're going to see today, is that we want to be doing so many things with the energy that's coming through. And in this case, I would say it's still a system that's far more advanced than a lot of the systems that you see on the market. But it is using all of the known technologies that we have today. There's no actual, like the novelties in the assembly. We don't have to actually invent a material for this to work. Next. Next, Christina. Yeah, sorry. In this case, we're actually inventing the materials. So on the right-hand side, oh, sorry. If you just, sorry, just with the, just with the advanced materials. This is just a whole other area of inquiry, and I think it's important, just especially for the younger architects in the room, to remember that on the left-hand side is a detail, let's say of an early detail of that icy solar facade system that you just saw. We were literally the kind of assemblies that we can put together ourselves, but like with very advanced optics, et cetera. And it does use less than 1% semiconductor of regular panels, so it's amazing from that life cycle standpoint. However, and much cheaper because you're replacing semiconductor with glass, plastic or glass. However, on the right-hand side is really where we believe things are headed in the 21st century, let's say. So I don't know how many decades it will take, but certainly we will be able to manipulate energy flows by manipulating the materials at the subatomic level. So what you're seeing here is a system that we're developing in graphene with multiple layers, where we were basically manipulating the geometry of the graphene at layers that are not even seen. So you see all this geometry on these layers, but it's literally a clear glass. And you can tell that clear glass and the graphene layers to do certain things, like let's say, let heat in but not light, or vice versa, or turn something into a display, or give privacy, or opaque or transparent, or whatever you need to do, let's say, with that interface. There's so many handles on the energy and on the functions that you have at the subatomic scale, i.e. the nanoscale, that you don't have at that macro scale that you're seeing on the left-hand side, where what you see is what you get. We see a plastic module, but it is redirecting light and is doing all these things, but it's actually a physical thing that is visible. Next. So just scaling up at the very large scale, this is an example of a competition that we did with Skidmore or Isabel. As you mentioned, we were working with them a lot on speculative projects, but also on built projects. And this is looking at how can you literally transform the climate. This was the Middle East, and where, if there's a lot of sun that you can collect, but you can't really spend much time outdoors. So this is looking at literally these larger scale solar collectors that are able then to create a complete microclimate underneath those umbrellas. But also it's you're outdoors, and you can also become a generator for the rest of the neighborhood. Next. Next. So this is just looking at an ecosystemic approach where we were looking at everything from airflow to the vegetation types to the water retention to water collection. So those big canopies were also obviously collecting water. And just looking at all of the different things at a much larger scale. So this is, as probably as large as we would go as district scale. Sometimes we are interfacing with folks from NASA and NOAA at the regional scale. So we go all the way up to regions and sometimes countries. But really, this is sort of our sweet spot. Is a few blocks at that district. You can do so much in creating a completely sort of self-sufficient ecosystem, if you will. Next. Next. And here's a project that actually got built. So this is Shop Architects, the Botswana Innovation Hub. And we had an amazing experience working on all aspects of the ecosystems in the schematic design phase on this one, including all of the flora and fauna, how we would, first of all, protect the savanna site that it was in, what kind of species would be specified, how would you work with this, we were calling it an energy and water blanket on the top, and then how would we retain the water through the section and generate power. We were also involved in the life cycle and material selections here, and including and especially the concrete, which was on-site processes and modular concrete. So you can see the vision of the savanna from the window. This is an early rendering, but you can see the concentration of biodiversity inside these courtyards, which is really come to fruition in the photos. Next. Hopefully we have some photos of this. This is, yeah. Yeah, maybe, and you can see how the floor plates were remaining very, very shallow so that we can actually power them through the icy solar facade. So this is a rendering of this icy solar facade that would be inside those clerestory windows facing north because this is the southern hemisphere. Next. This is, here you can see actually in construction, you can see already the concentration of flora and fauna and the roofscapes. You can go into the QR code there for more information about this project and the different systems and the different materials. But suffice to say that we would never have been able to take, we would never be able to take a project like this off the grid if it had the deep floor plates that are associated with tech projects. So I think that's another really, really important synergistic thing. You can have a high-powered combined heat and power at over 70% heat and high quality heat and power. But if you have deep floor plates, you'll never ever be able to run all the systems. So you can see here the very shallowness, the relative shallowness of the floor plates in comparison with the floor, with the clerestories peeking up from the roof to grab that the sun, because we're pretty far south in the southern hemisphere, and you can also see all of the sort of cooling and water retention on the roofs and in the courtyards. Next. I think this is probably the best one of the best examples where we parallel tracked what we call evolutionary architecture, which means we will get as many systems as we can into just in time delivery into this project, but then we will design it so that or co-design with the architects. Obviously, the architects are in charge of the overall design, but we will make the recommendations so that they could retrofit very easily with novel systems as they come online. So essentially, the macro design of the floor plates and the relationship to flora and fauna and water and sun is really a healthy one and a very productive one, from the sort of global morphologies. So as new systems come online, they're going to be able to evolve the whole campus for greater and greater net zero. Next.
And I'd say, speaking of flora and fauna,
over to you.
No, we've been, with Anna's group, has been looking at living systems for many decades now. And one of those systems is the active modular phytoremediation system, which uses plants and plant walls to remediate the air, remediate VOCs, and of course do carbon photosynthesis and carbon sequestration in indoor environments. One of the principles of this is that it's really an active system, drawing air through the root rhizosphere, where there's microbial activity that's really helping to, clean our air. And there's been many iterations of this. This also has some history with NASA research and sort of creating enclosures that can sort of breathe from within. We often talk about fresh air from within the building. We want to be able to reduce the energy that it takes to ventilate and heat and cool that air that's coming in. So if we can recirculate clean air in our buildings, we're really also reducing energy at the same time. And these designs have evolved over time and been featured in MoMA and in many other places. And we really, again, are thinking every one of our projects, we think at this multi-scalar level. We think about what it's doing at sort of at the scale of the globe down to what are we doing at the microbes of those, what are the roots systems and the microbes of the root systems doing, and how does that all impact and sort of compound on each other and influence how we were able to scale these systems and what do they mean and what influence could they have. And of course, as architects, which I think the majority of you are on this call, we've seen these images really crop up in the last, 20 years, even 10 years. And we kind of want to believe at all different scales, right? Room scale, building scale, urban scale. And we want to understand what is it that what kind of performances are we trying to get at it? So while the AMP system is one type of system, there are so many different what we call building integrated vegetation systems, everything from green roofs to green bowls and trellises, and of course our active indoor modular system. And all of them have different performances. And regardless of us drawing them, the mandates are coming for them. This is an older list of municipalities that are starting to mandate these things. And I think, we're we're headed towards more and more of this. So there has been a consistent body of research in many, many different fields in order to understand what is the performance of these systems. And we are doing an incredibly large amount of that research here at our center. And we're using that information that we get at the system scale. We're developing these systems, we're prototyping these systems, we're taking data, we're measuring them at a room scale or a zone scale. We're taking that information to bring that back to what kind of performances do we need to get out of those systems. We're projecting that into what does that mean for the impacts that it can have at an urban scale, whether that's energy or air quality or other things. And this is sort of the hope is that this research not only lives in sort of science in sort of science centers in multiple different scientific areas, but that we can understand its impact and influence so that we can start to understand how these systems can become more viable. And there's not only one way that we can value these systems. And one of the projects that sponsored also by the AIA was understanding how are we going to value these systems? How do we understand the value of them? And how do we understand the performance of these systems? And, as we said, there's many different almost siloed disciplines that are, someone is looking at water quality and stormwater management, and somebody else is looking at carbon sequestration, and someone else is looking at biophilia. And our attempt at an ecosystemic system is to understand how we can combine all of those things. So how can we look at all of these different typologies of building integrated vegetation and understand what about the designs of each of these things is impacting what kinds of performance? What are the mechanisms of those surfaces that grow things? And what are the design features that impact those mechanisms, whether that's photosynthesis or evapotranspiration or thermal resistance or water absorption or any of those things? And we're trying to project what all of those design variables, whether that's the choice of species or the choice of irrigation structure, or how much airflow is being pulled or pushed through the system, or in which direction, or what kind of growing media you're using, and what impact do all of those things have on each of these different aspects of performance that we're interested in. And why are we interested in all these aspects of performance? Because we have so many stakeholders in the built environment. We have the owners and operators, we have the designers, we have the occupants, we have the greater community, and all of them are sort of maybe interested in different things. An operator might be more concerned about how much energy reduction we can get if we're having a green roof, whereas the occupant is much more concerned about the air quality of their environments or the biophilic aspects of it, whereas maybe a municipality is interested in the biodiversity and the sort of increase of native habitat. So all of these things are important to various people, and we can achieve those in a living system that is designed to sort of perform. So we're tracking what are the performance indicators in each of these areas, whether that's CO2 or parts per million or VOCs. What are the different design variables? So for example, leaf area is going to be really important for photosynthesis. The more leaf area you have, the more carbon you can take out the atmosphere. The growing media is going to be really important in terms of how much air you can be drawing through the system and how much sort of surface area you have around the roots of the system to remediate air. Similarly, we can talk about thermal comfort and how it's impacting the thermal comfort, whether that's interior, exterior, microclimates, evapotranspiration. Acoustic comfort, that growing media, again, is going to be really important in absorbing sound, maybe more important than your leaf area. The impact on operational carbon is a really important one, and I think probably the most exciting one for a lot of architects, that it's more tangible. Can we really reduce the cooling loads of our buildings by having what's basically a thermal mass on the outside? And for municipalities, urban heat island effect is probably the number one reason why at least exterior vegetation, building integrated vegetation, is what is critical. And that also will depend on your growing media depth, your growing media porosity, your water holding capacity, what kinds of plants you're growing. If we're talking about what kinds of plants you're growing, sequestration potential, can it draw down more carbon? Well, what kinds of plants are you growing? Are they more woody plants? What kind of depth of the soil do you have? Do you have water holding capacity? All of this basically comes together Of course, we're interested in embodied carbon and the impacts that all of that can have on, the weight of the system, like the steel, all that water and soil. Does that potentially increase the amount of structural requirements of the system, or do we start using lightweight media and we can sort of reduce the embodied carbon? But as long as we're thinking about all of these things together, we can start to design more an ecosystemic system. So this was from our building materials in the climate report, where we really trying to put together all of those impacts on operational embodied carbon over time. And so what are the different impacts of this that we need to be thinking about, really think about it in a whole life cycle point of view. I won't go into the rest of these, but of course we're thinking about stormwater treatment and water treatment. Currently, water treatment using these systems also for water quality, and Mandy will go more into water quality, is something that we're really interested right now. These systems can produce food. What impact does it have on urban agriculture, biophilia, and generally ecosystems health for our environment? And all these things, if we kind of track them together, we can start to understand perhaps more and express more of their value, so we can work with them. And we're designing this with the AIA Future Forward grant from the Young Architects Forum and the Large Firm Roundtable. We're developing a building integrated vegetation toolkit to sort of speak to architects about, if you're considering these systems, what do you need to understand about them? What are you trying to do? And we, Yale CEA, are continuing to evolve designs. We're continuing to test. We're continuing to develop different aspects of it and test them in both isolated sort of chamber type experiments as well as in building projects. And this is a fantastic building project. It was completed a couple of years ago with SOM and CASE, which and Anna at Yale CEA. So we were able to integrate this beautiful AMPS, the active modular phytoremediation system, into the lobby of the Public Safety Answering Center. So this is a building that has to shut down or has to sort of close down in the case of an emergency. This is where this is where we would have first responders and people. Even in case of an emergency in New York City, the building has to shut down. The building has to sort of be on its own. And so the idea that we could circulate fresh air from within this building was a really important one. And as you can see, sort of the mechanics that went into going into supporting, the plant life in this wall is something, that is constantly evolving over time. These different designs are evolving over time.
Yeah, I would just say, before we get to the next one, just really quickly on that one, just to say that this is also a research test site where we're testing the comparison between air quality in two different large classrooms. And the mechanics that you see are a fraction of the mechanics you would need if you didn't have the plant wall. So what we're actually looking at, a lot of people see, oh, that looks really, extensive. And it is a lot, in comparison to what future systems would be, but it's designed as an experimental framework and system. Ultimately, the goal of these systems is to dramatically reduce not just the mechanical systems and energy, but the space that you need for the mechanical systems as well.
And the next area, water, is really tying together the water energy food nexus that we're more and more aware of within buildings, and really from an urban to regional scale, when we understand the interdependence between water, energy, and how that impacts, for instance, our access to food. If you go to the next slide. One of these ways that we could look at it is really understanding the water energy nexus in buildings, really through the facade. This area, the solar enclosure for water reuse. Not only are we questioning that water energy nexus in terms of how it affects resource security, the costs to households, and really the efficiency and means of moving towards net zero on site, but it's also really asking questions about water safety, water potability, really the true measure of water security in terms of access, availability, and safety. So if we go to the next slide. Here you can see really the position that this approach takes is really arguing for a shift to increase decentralization of our water management, different approaches that can operate at the household, building to neighborhood scale. Over the last 5 years, the typical household's water and sewer bills has increased by 24% in the US. And for instance, a state like California, over 90% of the electricity consumption is actually going towards the delivery, the treatment of water. So shifting to smaller systems, if you go to the next slide, where we can actually apply many of the both nature-based principles as well as the techniques that we have already used with conventional centralized water treatment, but making it more adaptive to its exact context. Really use principles of reclamation, of bio-based materials, renewable energy, and scaling available resources with local site-specific needs. If you go to the next slide. So here's an overview kind of conceptually of really the systems approach to interfacing with environmental resources in and around buildings and using it as a way to shape both heat, light, and our needs for safe drinking water to the occupancy directly. If you go to the next slide. Principally, the approach can take on many different embodiments. So maybe what you saw there was an application within a multi-story building in a dry climate such as Las Vegas. But really what we're understanding is the relationship between the resources and how we can best meet needs. So this overview of this matrix of different embodiments shows how in completely different contexts, there can be ways that we bring solar into the building. We concentrate that solar energy for different applications, really here focusing on water disinfection, and then also allow that optical shaping of the light for other multifunctional purposes in the building, such as cool daylighting, mitigating solar heat gain, and other thermoregulation processes that we would want to, and how we would use that available energy. Next. So for instance, here's one embodiment. You might think of it as a glass block module. Really, it's addressing a type of climate with it's responding to the angle of the sun. It's taking in solar energy and really concentrating it in different types of optical approaches, but then shaping how some of that cool light enters the building. We can work with different geometries and also different material properties, different surface applications, where we kind of spectrally use the qualities of the sunlight for different applications. Next. Here you can see more of a continental climate where you've got your geometry shapes and responds to the changing inclination of the sun. Next. Another embodiment, really ultimately to demonstrate different ways that it can be adapted for different sites. As we will show now on the next slide, there's an application we've been looking at and we'll be demonstrating as part of the Ecological Living Module program that we have with the UN, UNEP. But really, this is one embodiment that's actually taking a different approach and really looking at ways to make it as a low cost and viable for immediate household settings. So really adapting to conventional roofing assemblies and then really achieving what we're talking about, which is really providing safe drinking water, delivering heat through domestic water heating, and then also shaping cool light for the interior. So the next slide. One of the ways that we're really achieving a safe drinking water is through the novel incorporation of a photosensitizing dye that is part of emerging university research. In here you can see how the dye changes from pink to clear, and this is an indication of when water is safe to drink. It's very effective against viruses, so it really reduces the time that it would take to treat water, particularly in comparison to conventional solar-based disinfection techniques, providing year-round water safety. And that's really a goal for these types of systems, while also remaining user-friendly and accessible. Next. As with all the research, we work with different field testing models as well as different applications within different building test beds. Here you can see some example photos from sites in South Africa and Guatemala where we did a range of microbiological, thermal, and optical efficiency testing. And really how then all that characterization can really better understand also the building performance factors such as daylight autonomy, glare probability, solar heat gain. So we're really understanding how the system both works as a solar collector, solar disinfection device, but also as a window, and how it shapes sunlight and view, for instance. Next. And so, yes, to close, this is another embodiment that really what we're currently working on is the integration of novel ambient water harvesting materials. So we're really not only shaping sunlight, but actually shaping the material properties diurnally in terms of ambiently harvesting water and having sorbing and regeneration cycles in the geometry, programmed into the geometry itself. And the next slide, you can see a lot of this concept was published in the recent Fabricate 2024.
Yeah, so maybe to close, one might ask the question of why we're involved in the microbiology of water and other things. I think that the answer to that is we only have so much square footage on our buildings, and we need to do so much more in the 21st century with our buildings, and we want them primarily to be have overridingly architectural criteria, which means cultural and aesthetic and how we feel in our spaces, but they also have to be doing so much more than just sort of keeping the wolves out. We've got to be able to transform our energy and our water through these surfaces and through these assemblies. So the integration of these things, I think another thing just to note, we put the word health on our title. So it's really, I think, important to note that all of these systems, if you would look at the plant-based system, for example, we have gotten data back on preliminary experiments that we've had with subjects. There's a change in heart rate variability and breathing rates and other important health indicators in 20-something subjects within 1 hour of blowing air from the green walls into conference rooms and other and classrooms. And the subjects don't know that plants are even part of it. So they don't even know those are cases where we don't even show the plants. So there's no biophilia effect. We're controlling for that. But what the bottom line of that is saying is that we do need to design with ecosystems and with biodiversity because we've evolved over, the millennia to coexist with all of these other plants and animals and other and natural daylight and all the conditions of natural ecosystems. And so I guess that's sort of like on the bottom line, why do we work with so many other people that are not architects? But then also, I guess the question can be reversed and saying, why would architects get involved in designing with biodiversity and with all of these things? But I think, that's sort of the answer is that there's got to be this combination between culture and performance and science that is really synergistic. I don't know if we want to open up for questions.
Thank you, Anna. Thank you, Christina and Mandy. Yes, we are open for questions, and please feel free to put your questions in the Q&A tab at the bottom of the screen. Just to kick off, this discussion, I have a question myself, which is, regarding the integrated solar facade and the SEWR system. I feel they share a lot of common characteristics, right? Redirecting like solar energy and light. The question that I have is like, because these, elements have they're like multiple elements in different planes, right? There are chances of glare that could be perceived from the inside. So I was curious, like how does say each of these like manage glare?
Do you want to start with that, Manji, in the sewer, and then I can talk about icy solar?
Yes. So that's obviously very important to manage for wanting to capture as much energy and shape it for functional uses. There is always losses. There always some kind of reflective, kind of unplanned for effect. But with the last embodiment we showed you with sewer, it's sewer, the acronym, we actively tested for glare through a range of different testing mechanisms. And really you can see the how you can, when you compare it with a non kind of a control condition, the dramatic reduction in like spikes in kind of the solar transmittance, etc. And to really make it an even kind of more consistent condition where we call it cool light because we've really reduced the infrared and the heat. We've taken the heat off, but you're actually also kind of perceiving the daylight as softer. It's just you're getting ample light, but it's at a dramatically lower lux, and then the glare is controlled for with the like surface and geometric properties.
Yeah, actually, it's such a good question. We in the next instantiation of SOAR, which will be pretty limited, but we're going to be experimenting even with the lower layers with what we call transparent wood, but we're sort of another area that we didn't present today because asked us for the dynamic facades, but we also work on shift to bio. So looking at transparent wood or just translucent materials to kind of cut down on glare. In the case of the icy solar facade, it has a much, much greater concentration ratio. So we're working with concentration ratios between 4 and 500 in comparison to SOAR, which is only 1.5, right? We're literally, SOAR is a stationary system. We don't need very much elevation or concentration ratio in order to activate the chemical process that's happening with the sensitization of the dyes in order to neutralize the viruses. So we would only do as much as we need to do functionally for these things. We wouldn't do more. So the reason why there's a high concentration ratio in icy solar, because the overwhelming criteria of icy solar is to have the highest electrical output. So, for example, theoretically, indium gallium nitride cells or other types of concentrating solar cells that are very, very small, they can be beyond 80% efficient. So it's a really, really great efficiency. But the trick is that you have to actually track and you have to concentrate. And so you are going to have hot spots when you concentrate that much sun. And you probably see it in mirrored assemblies or giant concentrators. You have extreme light points of light. And so if you are in an area where someone might see that light, you do how we've done it is we have Kohler optics, which are basically like 4-quadrant optics that we put on top of that sort of ultimate hotspot that is then rediffusing it. You could rediffuse it, or you could literally just have a kind of translucent back shield that would protect the eyes from that front glare surface, which is the Fresnel optic at the front, and then the hotspot of the light. It's a great question. If you're very far away, right, let's say you're in a stadium, or we did one project with SOM, the Sheikh Khalifa Medical City, and it was very high up. And unfortunately, we weren't able to build that one because they canceled the project in general. But it was a really interesting project where we were really able to have that it was so high up and so far away from sort of the vision that the hotspots weren't a problem at all, and even the modules were open air. And why would we want that? Is just because then you get free ventilation. There was a way to ventilate the thing, and there was also just a way to reduce the number of parts in the things. So I think it depends on the application. I think there's some applications where a glare surface is acceptable, and many others, like an office, where it just isn't.
Great. Yeah, that kind of answers my question. Yes, I also wanted to follow up on that, but there is a question here from one of the audience. So it's saying like, so exciting to see these projects. Can you speak a bit about translating experimental and novel technology for a client at scale? For example, how do you adapt for their operations facilities team, engage with building code and building inspections and so forth?
I think this is definitely a question for Christina. She's an expert in this.
Oh,
All
well,
right.
I mean,
All right.
it's with anything novel, there's going to be some hesitation and considerations. But I think, one of the things that we're working towards is sort of, at some point these will respond to ASTM standards and so forth. And I think that when we do get to integrate them, and Anna, you could speak a lot more about how we integrate it into PSAC too, but I think, there is buy-in from many stakeholders, right? That
Yeah.
Everybody has to be sort of on the train with you, right?
Yeah, well, actually, so that is a very good point that you're bringing up, Christina, is that if something is kind of high risk, high reward, the first thing might be well, first of all, we have to mitigate risk. Obviously, we always have to have a best in practice system that's ready to go and can always mitigate the risk. You don't want the client to be putting on a lot of investment into something that will not have a backup. So if the whole building's being organized around it, then you have to make sure there's a just-in-time system. That's the first thing. The second thing is that in many cases, the discussion that we had a lot with our AAC partners is some clients are ready to accept that it's going to be much, much riskier to go with the status quo than to actually try to co-invest into something that will be next gen. We do believe that this is true, and PSAC 2 is a good example of that, but there was an alignment of stakeholders, which Christina is referring to, which started with the Bloomberg administration, as a client who was willing to waive the building codes for us to get started, the municipal building codes, because they, had that ability. And they also recognized that there would be a huge risk to putting up that building that had, as Christina mentioned, the programmatic requirement of turning off the fresh air intake in case of another 9/11 or Fukushima or a bioterror event or anything that would happen. It had to be a secure building. And it's not, all embassies and many high security buildings have that requirement, and they can really only deliver fresh air for, up to 10 days in the case of PSAC 2. So there is the possibility to see the status quo as like more high risk. California was a really good example of, where they're just starting to recognize that there's some of that data that we saw is that the catastrophic water shortages and potential for blackouts in many parts of the world. There's just not enough security in the energy water nexus to especially for the public sector clients. I think the public sector clients really need to lead in recognizing that the existing system and the existing status quo is higher risk than actually putting a little bit of investment into prototyping or testing a next gen or a radically more secure system, as what all of our systems are at the end of the day about human security on planet Earth, right? Like being able to literally, deliver potable water and air quality and secure energy on site. So I think that's the thing, is just to talk to them about like what is really secure and what is really experimental. We experiment on our own bodies every day, when we're in new environments and we're in indoor environments and we're changing our morphologies, we're changing our brains, we're changing our microbiome, we're changing all sorts of things about ourselves with the buildings that we inhabit now. So why not actually, recognize that and try to proactively, take control of that experimentation that we've been on since we've been living indoors majority of the time for, now centuries. So, so I think it's the risk factor. We have to talk about what is risk and characterize that. I also think that there's a way to talk about the near term, midterm, and far term possibilities for systems. I talked a little bit about evolutionary architecture when I showed the Shop Architects project in Botswana. They're very keen on this type of language of trying to say, okay, here's what it is now, here's what it might be in 15 years, and here's what it might be in 25, 30 years. Really starting to talk about that long term evolution. Some technologies went much further, faster and further than anyone thought they would. I would say solid state lighting is a good example of that. Right? We had projections of where solid state lighting would go and how it would change the energy consumption profile of buildings, and it went even faster. The problem is that it didn't. We now know that it's changing. It's having a catastrophic effect on the circadian rhythms of plants, animals, humans, even. We're not there yet with understanding what solid state lighting is doing to our environments. So we curtailed that research a little bit, short circuited it at the Department of Energy level in our country, and that was partially a marketplace thing. It was thought that the technology was done and ready to go and super low energy, and it is. So we can save a lot of carbon with solid state lighting. But what are we doing to our ecosystems? So I think that there's also there's some cautionary tales where stuff gets adopted very quickly, and we might have been more circumspect about having a little bit more data, about stuff. So we're all about the transparency, and we also believe 200%. PSAC 2 is a good example. Sorry, this is so long, but PSAC 2 is a good example where initially AEC team did not want to talk about toxins. It was post 9/11. The firemen and the policemen were our primary clients, and they stopped us on one slide where we were showing source emissions, and we talked on that slide about 45 minutes. They were delighted to talk about toxics because they knew so much about it, and they had been brutally affected in 9/11, and their unions had been brutally affected. So I think just being fully transparent about what world are we living in and what are the challenges. We strongly believe that many clients are not only able to handle the truth, but they're actually possibly like eager to push forward the ambition. We've actually seen incredible ambition coming from clients. In Botswana, it was the clients that insisted we not cut down the old growth savanna trees that you saw in those images. That was an amazing moment where we're like, yes, we're going to have shallow floor plates because of the client, and not because of other things. So that was an amazing. I think those are great examples of clients being really proactive.
Thanks, Anna. I really agree with that. Yeah, there's a big need for challenging the status quo, right? It's some people are doing it, some clients are doing it, but there is a bigger need for people to adopt all these kind of newer technologies, right? We have kind of a minute left, so I actually had a question about the AMP system. So I wanted to ask, like, how does this, get scaled, like, for extreme environments? I know this is on the interior, but uh, how does the system adapt to kind of like high demand environments like office spaces kind of, and then can this like be modularized into existing facades, right?
Yeah, absolutely. We're doing, and we've been doing testing in office environments. And Anna mentioned one test scenario where we had a conference room of 16 people, and it was a modular system. So we had a scale, a scale associated with that, like how much leaf area, how much growing media, and such, was the rate of air change, and we were able to show, as Anna mentioned, the sort of drastic reduction in carbon dioxide in the room without having to use the traditional ventilation systems. And we're also doing some experiments in New York City in an office environment. We're monitoring all of these factors together. So how much of a system, and it's not just how much square footage, because every design could be different in that way. It's really more about maybe the leaf area or the growing media, or how those plants is raised, or what kind of watering regime it has, how much light it has, what's the species of the plant, and how does it react to that light. So all of these factors, not just the scale and the modularization of it, but all of those factors will contribute to sort of that idea of scale. And how many people, and what are those people doing? Are you putting it in a gym, or are you putting it in a place where people are stationary? So I think that is sort of the work of our center, is to sort of understand those relationships, and so we can make that sort of scalar comparison and understand just how much talking about for what purpose. Yeah.
We should credit our sponsors before we go on that system, because the one that Christina is mentioning is being sponsored by Shop Architects and Fresh Air Building Systems. So they've been co-designing and also giving us a lot of spaces to gather data for that information.
It's great. Big shout out to them. All right. It seems like we're a bit out of time here. Thanks a lot, Anna, Christina, and Mandy for presenting to us. This has been great, right? It's a lot of new and fresh ideas. I'm sure like people have a lot of like takeaways from this and research further into this, about the possibilities and pushing the status quo, right? Like trying to adopt some of these in their designs as feasible, right? Like however they feel it's feasible. Anyway, so thank you everyone for attending. And I don't see any other questions here, and we also ran out of time. So thank you all, and have a good day.
Thank you very much.
Thank you so much,
All right.
everybody.
Yep.
Have a nice day.
Thanks.
Bye-bye.